so we continue with this proof. So let me point some let me write down something here that I probably said but I didn't write down. So you are looking at the open cover of X centered at the points x1, x2 and so on of X. So which open cover is it? It's the open cover consisting of open balls of radius delta. Okay, that's something I didn't write down, so let me write it down here. So look at the open cover of open balls of radius delta. So you look at the open cover of this space X, of the metric space X, which we have assumed compact. Okay, and you are looking at the open cover which consists of open balls of radius delta, that is this delta that we have chosen, that we have gotten above, corresponding to the epsilon, or rather epsilon by 3, okay, because of equicontinuity. Okay, so and for the open cover you are only looking at balls of radius delta, and the centers are not, of course you could have taken the centers to be all points of X, but then you take the centers only among the points x1, x2 and so on. That's that's the countable dense subset of the metric space that we have cooked up. Okay, and so this is actually in principle this is a delta net for X, and X is compact, so it's totally bounded. So it so what I'm saying is it's not a delta net, it will give rise to a delta net because it's an open cover of open balls of radius delta. Okay, and because of compactness this open cover will give rise to a finite subcover. So those finite subcover will be centered at finitely many points which are among these xi's, and we label those points by xi1, xi2 etc. xim, and you take the open balls of radius delta centered at each of these finitely many m points, and you take the union, you get X. That's so this collection of points, finite collection of points among the countable dense subset, okay, this is a delta net. This is a delta net for X. Okay, and well, we'll have to work with this. So what we'll need to show is that we need to show that we have to show that this the whole idea is to show compactness of a family of functions. So we started with an arbitrary sequence and then we tried to verify sequential compactness, and we have gotten hold of this subsequence, this GNs, okay, by the diagonal argument, and we have to show that this subsequence converges on all points of X, at all points of X, okay, and uniformly, and mind you, the subsequence has already been cooked up in such a way that it converges on the countable dense subset. Okay, now so I will have to show this for every small x in capital X. I will have to show that for my given epsilon you can choose n and m sufficiently large, namely greater than or equal to a certain capital N, such that the distance between Gn and Gm at X can be made less than epsilon. Okay, that is you are just verifying that the sequence of GNs is uniformly Cauchy. Okay, and uniformly Cauchy means Cauchy with respect to the supremum norm, the metric induced by the supremum norm. Okay, so the point is that how do you get to an arbitrary point of X, whereas the GNs are converging only on these points, which are points among a countable dense subset. Okay, you have to interpolate with the x's with the xi's. All right, that's what you'll have to do, and it's done very easily by the triangle inequality. So what will happen is that, see, now you take any for any x in X, okay, there exists j such that the distance between X and Xij is less than delta. This is true. That is because these xij's xi1 through xim, that is a delta net, alright. So there is such a j, so pick that j, take the corresponding xij and you interpolate with respect to that xij. So now you can write out the triangle inequality. What you will get is, well you are going to get distance between g n of x and well, so I want to look at gn of x minus gm of x. So that is what I am going to write out. Oops. The distance between gn of x and gm of x is that now you introduce that xij which is within a delta of x. So you write this as this is less than or equal to gn of x minus gn of xij plus gn of xij minus gm of xij plus mod gm of xij minus gm of x. So this is how you split the triangle inequality, okay. You extrapolate, I mean you interpolate the x back to itself by this xij, and then you introduce this minus gn of xij plus gn of xij minus gm xij plus gm xij, okay. And now the point is that this, now you see what you will have to understand is that the see, because of you see in the first term it is the same function gn, alright, and by equicontinuity of the family, okay, the distance between function values for any function in the family is going to be less than epsilon by 3 if the distance between the arguments, the variables, is less than delta. So you see this is already less than epsilon by 3, okay, and so is this. So the first and the third term are already less than epsilon by 3. That is because of, this is just because of equicontinuity, due to equicontinuity. Mind you, the equicontinuity has already been assumed for all functions. So these are certain functions in that family, so it holds for them as well. And then so the first term and the last term are fine. They are going to give me an epsilon. They are going to be lesser than epsilon by 3 each. The problem that I have to worry about the middle term, but the middle term is not a big problem, because actually you know the GNs, the sequence of GNs, it converges on the countable dense subset of the xi's, which is labeled by the points x. Therefore these GNs are going to converge at xij certainly, okay. So you see, so how do you deal with this? You see, GNs converges on the countable dense subset consisting of x1, x2 and so on. So in particular it will converge on this finite subset, okay. So in particular on the finite subset which is given by xi1 etc. up to xim, and of course you know the xij that I have chosen is inside this finite set, okay. But then the point is that by definition of convergence of a sequence, I can certainly find an n, a capital N, such that small n and small m greater than capital M will make sure that this quantity is always less than epsilon by 3 irrespective of the xij that I choose. That is because there are only finitely many. You will get one bound, one subscript for each j, and then you take probably the maximum amongst all those, okay. So so there exists n such that n comma m greater than n implies that the distance between gn of xil and gm of xil can be made less than epsilon by 3 if for all L varying from 1 to m. Okay. So this can be done because it can be done for each xi, it can be done for xi1, it can be done for xi2 and so on, and for each you get an integer and then you take the maximum amongst all those. Okay. They are only finitely many, this can be managed. So that is it, then you are done. What this will tell you is that if m and n are greater than n, okay, then what you will get is that the left hand side, which is gnx minus gmx, is less than epsilon. Okay, and mind you, this is independent of x. Okay, this has got nothing to do with x. X didn't matter, right? So this is independent of x. So this sequence Gn is uniformly Cauchy. On x, and that is the proof of the theorem. That ends the proof of the theorem. Okay, so we have demonstrated sequential compactness. So to complete the proof accurately, what we have shown is that we have shown that Gn is uniformly Cauchy. Okay, but the Gns come from this subset which is already a closed subset. Okay, so but it's a closed subset of a complete metric space. Therefore it's also complete, and therefore showing that as the Gns is Cauchy is the same as showing that the Gns are convergent, the sequence of Gns is convergent, and that is what you wanted. We started with an arbitrary family, arbitrary sequence of functions from the subset, and we have produced a subsequence which converges. Okay, so that is the Arzela-Ascoli theorem, right. Now what we need to do is that we need to now go back to complex analysis and look at the kind of functions that we are interested in. We are interested in analytic functions, and then we are interested in, of course, meromorphic functions. That is our final aim. So what does it mean for meromorphic functions? So the beautiful thing is that I mean to begin with, at least let us say analytic functions. The beautiful thing is that see the main point is the following. What does Arzela-Ascoli theorem say? It says that if you are, for example, looking at continuous bounded real valued functions on a compact metric space, then if you want a compactness of a subspace, that is a collection of functions, okay, then that is equivalent. Of course that subspace has to be closed and bounded, because compactness always implies closed and bounded. Okay, but what you need to put extra is equicontinuity. Okay, so basically you need boundedness, you need a closed for a closed subset to be compact, you need it to be bounded, and it has to be equicontinuous. That is what you want. Okay, and mind you, this is a nice thing, because it's easy to equicontinuity is more friendlier to check rather than checking something like the total boundedness, which is very, very difficult to check, okay, for a family of functions. It's not so easy. Okay, so now when you go to the context of complex analysis, and if you are looking at analytic functions, what happens is something very beautiful happens. See, what you get is, analytic functions, for analytic functions you have the Cauchy integral formula, you have the integral formulas. See, these integral formulas, if you apply the so-called integral inequality, the ML inequality, which says that the modulus of an integral is bounded by m times L, where m is the maximum modulus of the integrand on the contour of integration and L is the length of the contour of integration. Okay, this is the ML inequality. If you apply these ML inequalities to the Cauchy integral formula, what you get are called the Cauchy estimates. Okay, so the beautiful thing is that for analytic functions you have Cauchy estimates. Okay, and what these Cauchy estimates will tell you that is that if you are working on a compact set, okay, it will tell you that the derivatives are bounded. Okay, because mind you, the derivatives of an analytic function are given by the Cauchy integral formulas. The general Cauchy integral formula will give you the nth derivative. Okay, so if you therefore the bounds for the derivatives are given by applying the ML inequalities to the Cauchy integral formula. So what happens is that if you have an analytic function on a compact set, for example on a closed disk if you want, then all the derivatives are all bounded. okay, all the derivatives are bounded. So what happens is that in some sense you get boundedness of derivatives, but the beautiful thing is once you have boundedness of derivatives, that always implies something stronger for the original functions, it implies equicontinuity. So what happens is if you are working with analytic functions, equicontinuity is automatic, okay, equicontinuity is just automatic. So therefore what happens is that just uniform boundedness will give you sequential compactness. That is the big deal. The big deal is equicontinuity comes for free if you are going to work not just with continuous functions, but if you are working with analytic functions, okay, that is the philosophy, okay, that is the direction in which I am going to explain how these things work. So let me make this, so in that generality, the theorem, the version of the Arzela-Ascoli theorem is a very important theorem, it is called Montel's theorem, okay. So we go on to Montel's theorem, which is the key ingredient for proofs of many important theorems in complex analysis, including of course the Riemann mapping theorem and the Picard theorems and so on. So let me put this Montel's theorem. So here is Montel's theorem. So let D in the complex plane be a domain. Of course I am always assuming it is an open connected set and it is non-empty, of course, okay. Let script f, so let script f be a family, you can call it as family or collection, whatever you want, be a family of analytic functions on D, which is normally uniformly bounded. On D, okay. So what is this normally uniformly bounded? Whenever you say for a certain property, if you say normally that property, it means that that property is to be verified not for all sets, but it's to be verified only for compact subsets, okay. So when I say normally uniformly bounded on D, it means that it's uniformly bounded on compact subsets of D, okay. So let me write that is uniformly bounded on compact subsets of D. So I am using abbreviations UFLY for uniformly, BDD for bounded, CPT for compact, okay. So suppose it is normally uniformly bounded, okay, then you have sequential compactness, okay, then you have compactness basically, okay, but the only thing is that you should see compactness as sequential compactness, okay, and the sequential compactness in normally what does it mean? It means that given any sequence you have a convergent subsequence, but the only thing is here it is not just convergent on the whole, it will be you will get a convergence, okay, which first of all it is a convergence of a sequence of functions, so it will be normal, it will be a uniform convergence, okay. Mind you, whenever you are talking about convergence for functions, it is always a kind of uniform convergence, alright. For example, that is how it is if you are looking at the continuous complex valued or real valued functions on a compact metric space, okay. So it is uniform convergence, but it is not again just uniform convergence, but it is uniform convergence restricted only to compact subsets. So it is uniform convergence in the normal sense, okay. So that is the kind of sequential compactness that you will get. So that is the result, okay. Then every sequence in F has a subsequence that converges uniformly on compact subsets of T, okay. There are several little subtleties in the statement statement of this theorem which I will try to explain. Okay. Now, So let me give you, let's go to the proof of this. Okay. So what I want to tell you is that, you see, in how do you contrast this with respect to the usual Arzela-Ascoli theorem? See, the usual Arzela-Ascoli theorem is for functions defined on a compact metric space. Okay, that's the first thing. Then the second thing is, in the usual Arzela-Ascoli theorem, whenever you are talking about convergence, it is uniform convergence. Okay, it is just uniform convergence. It means uniform convergence on the whole space, right? And the third thing is that the Arzela-Ascoli theorem there is that if you want compactness, which is the same as sequential compactness, okay, that is every sequence has a convergent subsequence, that for that you will have to give boundedness, which is actually uniform boundedness, okay, plus you have to give equicontinuity. Okay. Now the big deal is when you come to complex analysis, when you come to analytic functions, I have already told you that the problem with analytic functions is that the convergence always is never uniform on a domain. It is only uniform when you restrict it to compact sets. So you have to change the convergence to normal convergence. So you must not require always convergence, you should require convergence only on compact subsets. Okay, that is the first change you have to make. The second change is that you can get rid of, you do not need equicontinuity. Okay, and so you just get in a sense you are saying that uniform boundedness implies sequential compactness. That is what you are saying. Okay, but the beautiful thing is that the sequential compactness is with respect to normal convergence. Okay, that is one important thing. The other thing is the functions are not defined on a compact set, they are defined on a domain. Okay, that is another difference. In the usual Arzela-Ascoli theorem, you are looking at functions that are defined on a compact metric space, whereas here you are looking at analytic functions which are certainly continuous, but they are defined on not a compact set, they are defined on an open set, open connected set. Okay, that is the difference. These are the differences. So now but you can see that the point is that you are able to, when you come from the from the topological side to the complex analysis side, okay, you replace convergence, uniform convergence by normal convergence. You forget equicontinuity because it comes for free. Okay, so how does one prove this? So the proof is very simple. The first thing I want to tell you is that if you are looking at a compact subset of the domain, then there is nothing great because you can directly apply Arzela-Ascoli theorem. Okay, and you have to use the bounded the Cauchy estimates. Okay, so for example, let me tell you. So suppose Z0 is a point of D. Okay, let rho be greater than 0, so that the disk mod Z minus Z0 less than or equal to rho is in D. Okay, you choose a sufficiently small radius so that the closed disk is inside D. All right. Of course, I can always find since Z0 is a point of D which is an open set, I can always, it's an interior point, so there is always a disk, open disk surrounding Z0 which is also in D. Now you take a disk of slightly smaller radius, okay, and that closed disk will also be in D. Okay, you can take that as your rho. Okay, so the reason for taking the boundary also is pretty well, because then I get a compact set, because a closed and bounded set, so it's compact, and once it's compact I can apply all the hypotheses I have. So now what happens is, watch that, if I take this, if you take the family, if you look at a family of analytic functions on D and you restrict it to this closed disk, okay, what you are getting is a family of continuous functions, complex valued functions. Mind you, analytic functions are continuous, of course. Okay, they are complex valued continuous functions, and you are restricting them to a closed disk which is a compact subset. It is also a compact metric space. So actually, you are in the situation of Arzela-Ascoli theorem. The Arzela-Ascoli theorem actually needs only continuous real or complex valued functions defined on a compact metric space. Okay, so you are in that situation. All right. So since you are in that situation, you are already given that this family is normally uniformly bounded. It means that it is uniformly bounded on compact subsets. Therefore, this family is bounded on this closed disk because it is a compact subset. So you already have boundedness, you have boundedness of the family which is actually uniform boundedness, okay, you have that already. Now what more do you require for extracting a convergent subsequence from a given sequence? What you require is that you require equicontinuity, okay, but the point is that because of analyticity and the Cauchy estimates, equicontinuity is automatic. So let's see why that is true. You see that so let me say the following thing. Well, if Z prime is in the set of all Z such that mod Z minus Z naught is less than or equal to rho, okay, you take a point here, and then you see what will happen is, so you know, if you want, let's take something that that is right. So yeah, fine. So what you do, so let me draw a diagram so that it's easier to visualize. So here is my Z naught, and here is my closed disk centered at Z naught radius rho, and here is my Z prime, okay. Now what you do is that, well, so notice so you can see, you know, you can choose a delta such that the closed disk centered at Z prime radius delta lies inside this closed disk, okay. So I can choose a delta like this, okay, choose delta greater than 0, so that mod Z minus Z prime less than or equal to delta lies in mod Z minus Z naught less than or equal to rho. You can do this, okay, and then now you do the following thing. You look at look at the Cauchy integral formula. See, by the Cauchy integral formula, well, this is the second Cauchy integral formula, which is for the derivative, first derivative, f dash of Z prime, okay, is what? It is 1 by 2 pi I integral over integral in the positive sense over this circle mod Z minus Z prime is equal to rho delta, okay, of f Z t Z by Z minus Z prime, alright, and I am going to get the whole square, okay. This is the first Cauchy integral formula, right, or rather second Cauchy integral formula, okay. The first Cauchy integral formula is for the function itself, which is a zero, think of it as zero derivative, okay. So this is a Cauchy integral formula. This is true for all functions f in f. This is fine. This is because after all f is a family of analytic functions, so this is true. Now you now apply this. I am just trying to write out the Cauchy estimate. So mod f prime of Z prime is what? This is going to be modulus of this integral, but that's less than or equal to the maximum value of the integrand multiplied by the length of the contour, which in this case is the circle of radius delta, okay, centered at Z prime. So what I am going to get is I am going to get so this is less than or equal to, I am going to get 1 by 2 pi is what I am going to get if I put a mod here, and the length of the contour is, well, it is a no, if you put a square, then it is an f prime. If you put, so what is the Cauchy, what is it? See, f naught is if you put a, this is the first formula. So if you want the nth derivative, you have to put n plus 1. Okay. So what is this? So I'll get, see, if I calculate the modulus of this, I'll get mod f z. Okay. So let me put m here. So for the modulus of fz, I'm going to get an m. Okay, and then for the mod z minus z prime the whole squared, see, that is mod z minus z prime is delta, because the variable of integration is z, and the variable of integration lies on the region of integration, which in this case is this contour, which is positively oriented. This is the orientation, the usual positive orientation. So this is m by delta squared. Okay, and I'm going to get the length of the contour, and that's going to be 2 pi delta. Okay, so basically I'm going to get m by delta. And what is this m? See, this m is the common bound for all the functions in your family on this closed disk, on this big closed disk. That's because that's given. You see, you are given that, go above and look at this. You are given that this family f is a family of analytic functions. It is normally uniformly bounded on D. So it means that it is uniformly bounded on every compact set, on every compact subset of D. So on this closed disk of centered at z0 and radius rho, which is of course a compact subset of D, it is bounded. Okay, all the functions are bounded, and I am taking that bound to be m. So let me write this, where m is the uniform bound for all f in the functions f in this family script f on this disk centered at z0 radius, closed disk with radius rho. Okay, you can put this bound independent of delta also. Okay, so you can, so this delta that I chose seemed to depend on the z prime. All right, but then you can get rid of this delta so that I can get a uniform bound for the derivative f dash is as follows. See, the first thing that you can notice is that I can change this contour of integration, which is this smaller circle centered at z prime and radius delta, to the larger circle, which is mod z minus z0 is equal to rho. And I can do that because of the fact that f is analytic in the bigger closed disk, and also the point z prime is also enclosed by the bigger circle. Okay, so therefore this formula for f dash of z prime is valid. Okay, so in this way I have gotten rid of the delta in the integrating contour. Okay, then the other thing is I will have to get out the delta here appearing the bound here, and so for that what I will do is that I will just have to restrict z prime to be inside a a circle of radius rho by 2. Okay, centered at z0. So restrict z prime to mod z minus z0 less than or equal to rho by 2. Okay, if you do this, then you see this effectively makes this delta, which is supposed to be the the distance between the point z, which is on the contour of integration, and the point z prime, which is inside the contour. This distance from z to z prime, what will it be? You see, the z is now going to lie on the outer contour, the outer circle, and there is z prime inside. Okay, and you see the minimum distance between z and z prime is rho by 2, and therefore so this delta here will essentially be this delta is supposed to be the distance between, it should be modulus of z minus z prime. Okay, and that distance is at least rho by 2. All right, and of course therefore 1 by delta squared will become less than or equal to 4 by rho squared. So basically, instead of this delta squared, I will get a rho squared, and I will get a 4 here. Okay, the inequality will get reversed if you take reciprocals, and of course this this 2 pi delta will become 2 pi rho, because that is the length of the contour, which is the length of the outer circle. So in effect, this bound will become 4m by rho, okay, and that will become a bound that has got nothing to do with delta. All right. Now, you see, of course, m is the uniform bound for all the functions in the family on the bigger closed disk, centered at z0 and radius rho. But what does this give you? You see, now you calculate what is f of z1 minus f of z2. Okay, what will this be if you take z1 and z2 inside this to be two specific instances of z prime. So here is z1 if you want, and here is z2. Okay, and of course, you know, this integral is going to be independent of the path, so long as the path is inside this closed disk. That's because f dash is analytic there, and what will happen is that, you know, you're going to get this is by the ML inequality, this is less than or equal to integral from z1 to z2 mod f dash of z dz mod dz. And now, you know, this, now you can apply this bound. This mod f dash of z is less than or equal to 4m by rho times this mod dz is going to give you mod z1 minus z2, and that is for example, if you take the straight line segment from z1 to z2, okay, and this is valid for all z1 and z2 in this closed disk mod z minus z0 less than or equal to rho by 2. Okay, so you see, what does this tell you? This tells you that the I can make the distance between fz1 and fz2, you know, small. The moment small enough, the moment I can make the distance between z1 and z2 small enough. Okay, and this is, and in a way that is independent of the particular choice of z1 and z2. Okay, and also in a way that has got nothing to do with the function f, because this m is a uniform bound for all the functions. Okay, and that is exactly saying that f, all the functions f, the whole family of functions script f, okay, that is equicontinuous on this disk centered at z0 and radius rho by 2. Okay, and that's how you get equicontinuity for free. Okay. See, the last inequality tells you mod fz1 minus fz2 is less than or equal to some constant times z1 minus z2. Okay, so what that gives equicontinuity. That's like a Lipschitz condition. You see, given an epsilon, you choose carefully the delta, and the way you choose delta is independent of z1 and z2. So independent of z1 and z2, you are saying the distance between f of z1 and f of z2 can be made lesser than epsilon whenever z1 and z2 are within a delta, and independent of z1 and z2. That is equicontinuity. See, it is actually, it's beautiful. It's uniform. It's a kind of uniform continuity, because you don't worry about whether it is z1 or which z1 or z2 it is, and it also works for all functions f. So it's a kind of uniform equicontinuity. That's what you get. I mean, that's the power of this of the Cauchy integral formula that you're using. Okay, and this is what you get if you assume analyticity. You get this. You get equicontinuity just like that. Okay, so the only thing that is left is uniform boundedness. Okay, but that's already assumed. So you get sequential compactness, but in the normal sense. That's the point. That is Montel's theorem.